Okay, so in this lecture, I want to tell you about two more examples of groups, namely the dihedral and quaternion groups. And these examples illustrate two important ways of giving groups. So ways of giving groups. So one way, an important way, is as symmetries of an object. Okay, so in the examples that you've already seen, we've seen this way of giving a group as symmetries. So for example, this symmetric group Sn, this is given as symmetries of the set 1, 2, up to n. Or another example that you have seen, the group GLN F of invertible matrices over the field F. This is symmetries of the vector space F to the n. So now, what are dihedral groups? So the dihedral group D2n, which has cardinality 2n, this is the symmetry group of a regular n-gon. So here n is an integer. I will take it to be at least 4. Okay, no, I will take it to be at least 3. Okay, so what kind of symmetries can we have of a regular n-gon? Well, we can have rotation, and we can have reflections. And in fact, you can see that any symmetry of the regular n-gon can be obtained by composing a rotation and a reflection. So any symmetry is a composition of these two types. So now I said that the cardinality of this dihedral group D2n is 2n. So let's think about that. And let's maybe do that by drawing an example. Let me try to draw the case n equals 5. Okay, so this is a pentagon that's not too far from looking regular. So now let me take a vertex. Maybe I take this vertex, and I suppose I have an element S, a symmetry in this dihedral group, n equals 5. So this is D10. Then well, what can happen? By composing with a rotation, I can assume that S maps this vertex V to itself. So by composing with a rotation, can reduce to the case that S of V is equal to V, and then if S maps V to V, then either S is the identity, meaning it fixes all the vertices, or S is the reflection about the line that starts from V and cuts through the center. So let's try to draw the picture again. So I have, if this is the center, I have this line, and I have the reflection S like this. So it's interchanging these two vertices and these two vertices and fixing this one. So now if we think about how many elements this group D10 has, so for the original rotation, I have 5 possibilities. I can map V to any one of these 5. So the cardinality of D10 is 5. This is possibilities for the rotation times 2, and this is when S of V equals V, if S equals the identity or S is a reflection, the reflection that we just described here. So in total, I get 10, and you can see that for a general N, you will similarly have N here, possibilities for the rotation, and still 2 for either the identity or the unique reflection fixing the vertex V. Okay, so this is one way to think of this dihedral group. Now there is another way to think about it, which gets at another way of giving a group. So another way to present groups is by generators and relations. So what do I mean here? Here I mean that I give myself some, well, let's do it in this example of the dihedral group. So the dihedral group D2N is the group generated by an element X and an element Y, subject to the relations that X to the N is Y squared is the identity. And if I conjugate X by Y, then I get the inverse of X. Okay? Now, so here, at first, I think to a lot of people, the idea of giving a group as symmetries is more natural than giving it as generators and relations. Here with generators and relations, it's important to note we are just saying X and Y are formal symbols satisfying these relations, and that's okay. We are not forced to give a geometric interpretation to X and Y, although we can, because thinking over here, we can think of X as a rotation by angle 2 pi divided by n, and y as a reflection, like this reflection, okay? So here in this concrete case, you see the two different ways of giving the group. Now, a couple more things to remark about these dihedral groups. So if we look at, let's do the smallest non-trivial example, D6. So this is the case of a triangle. If you look at the case of a triangle, 3 vertices, then you notice that preserving the structure of the triangle imposes no extra conditions. For example, here in the pentagon, if we say that this vertex V maps to itself, then this vertex here, it has to remain close to this one. So either it stays where it is, or it has to go to that one. That's how we made this argument here. Here, there's no conditions like this. So we are allowed to do an arbitrary permutation. So arbitrary permutation of the vertices works. What does that mean? That means that this group D6 is naturally isomorphic to the symmetric group S3 on these 3 vertices, 1, 2, 3. Okay, so now I've told you about 2 ways of thinking about the dihedral groups. One in terms of generators and relations, one geometrically as symmetries of the regular n-gon. I'd like to now tell you about a different but related group called the Quaternion group of order 8. Q8 of order 8. It's very useful as an example of a group with special properties. You will see this on the homework. Okay, so let me describe this group to you using generators and relations. It's also possible to describe it geometrically, but I'm not going to do that here. So this Quaternion group of order 8, in terms of generators and relations, it is generated by 2 elements I and j, subject to the relations that I squared is equal to j squared is equal to an element we'll call -1, and ij I inverse is equal to j inverse. So when I write this element -1, it satisfies the usual rules for multiplication that you are used to with -1. So -1 squared is equal to 1, the identity of this group. And for example, -1 times I is equal to I times -1 is equal to an element that we call -I. So using these rules, it's easy to write down the 8 elements of this Quaternion group of order 8. They are simply 1, -1, I, -I, j, -j, k, and -k, where, so this is at the set of these elements, where here k is a shorthand for the element I times j. Okay? So, what can we say from this? Well, one thing I want to point out is there is a simple way using a circle or a clock to remember how to multiply any 2 of the 3 elements I, j, and k. So what you do is the rule is clockwise, no sign, and counterclockwise you introduce a minus sign. So what do I mean by this? Suppose I want to multiply j times k. So I'm doing first j and then k. Well, I look at the order in which they appear on the clock. First j and then k. This is going clockwise. So their product is the next thing on the clock, which is I, without a minus sign. But if I multiply the same two elements in the other order, k times j, well, now if I look what's happening on the clock, I have first k and then j. I'm going counterclockwise. So the next thing is I, and I introduce a minus sign, so the product is minus I. Okay? Now, from this simple rule, we deduce several things. So Q8 is non-abelian because we see here are two elements, j and k, and they do not commute with each other. And more precisely, the center of Q8 so remember the center, this is the those elements of the group that commute with all the elements of the group. This you can check is just the set consisting of plus or minus 1. Because the 6 elements I minus I, j minus j, k, and minus k, they do not commute with everything else. If I take one of these 6 elements and I take another one that's not the negative of the first one I took, those two will not commute. Okay, now let's compare to the dihedral groups. So which dihedral group is going to be most closely related to the Quaternion group of order 8? Well, as you guessed, it's going to be the dihedral group of order 8, the dihedral group that has the same order. So note D8 and Q8 are both non-abelian groups of order 8. Now, over there, we saw that the center of Q8 consists of 2 elements plus or minus 1. What is the center of D8? Remember, D8, this is symmetries of the square. What is the center of D8? Well, using our description of D8 as generated by x and y with x to the 4th equals y squared equals the identity, and yx, y inverse equals x inverse, it's not hard to check explicitly that the center of D8 is exactly the set consisting of the identity and x squared. Okay, so yeah, I will leave this to you, and you also have a homework problem about more generally finding the center of all the dihedral groups. So the center of Q8 and the center of the dihedral group of order 8 are both of order 2. So we see more and more properties that they share in common. We can ask now, are Q8 and D8 isomorphic? Well, what is to study this further, we can make tables of the number of elements of each of the groups of a fixed order. So if we have two groups and the number of elements of order 2 is different for those two groups, for example, we immediately know those two groups can't be isomorphic. If our two groups have the same number of elements of order 2, it doesn't mean that they're isomorphic. It means we have to look further. So let's make a table for D8. Let's have the order of the element and the list of elements of this order. So, well, the order is 8. The order of an element divides the order of the group. These groups are not cyclic, so the order of an element of D8 can be 1, 2, or 4. If I look at elements of order 1, every group has exactly one element of order 1, the identity. Elements of order 2 in D8, well, it's most of them. We have y, x times y, x squared times y, and x cubed times y. So we have 1, 2, 3, 4, 5. Let's maybe add a third column, list of elements, and then the number of elements of this order. So we have 1, 5. Finally, we can have elements of order 4. X and x cubed have order 4. So I have two elements of order 4. And now, as a check, it's always good in these computations to check, because we tend to forget elements. We add these up, and we have 8. So that's a good sign that we didn't make a mistake. Now let's do the same thing for the Quaternion group of order 8. So I have the order of element, the list of elements, and the number of elements. Okay? So again, I have, if the order is 1, then it's the identity. If the order is 2, in this case, it's just the element minus 1, the identity that I was calling 1 in this case. So the number of elements is 1. And in this Quaternion group of order 8, there are loads and loads of elements of order 4. So plus or minus I, plus or minus j, and plus or minus k, these are all elements of order 4. Why, if you square one of these, any of these, you get minus 1. Because you get minus 1 and not 1, it means that these are not elements of order 2. If you take the 4th power, you get the square of minus 1, which is 1, so they have order 4. So we have 6 elements of order 4. So now we can, so conclusion, for example, we can say D8 has 5 elements of order 2. Q8 has only 1. Therefore, D8 is not isomorphic to Q8.